Okay, I'm going to talk about chaos theory. For what comes to mind is Jurassic Park, where that guy puts a drop on that girl's wrist and it falls in different directions, and basically made an assessment of why it did that. Those all these variables associated with the curvature of the wrist, hairs on the wrist, blood vessels, imperfections of the skin, and so on and so forth. Okay, basically you have degrees of freedom. Here's water. It could rotate this way, it could rotate that way, it could rotate this way. It could also move. I think it has 3n, where n is the number of number of atoms. So you have 1, 2, 3. So it's 8 degrees of freedom. In this case, 3n minus 1. In chemical systems, here it's a physical system. You have this kind of motion, this kind of motion, this kind of motion, this kind of motion. So that lends to the degrees of freedom in statistics also. It's a statistical term for just measuring parametric, multiple parameters associated with a system. Okay, here you have chi-squared in statistics. Basically, chi-squared is used in tables to relate one data set to another. Here you have r-squared in a linear regression. And you can use chi-squared as r-squared, but you can't use r-squared as chi-squared, because chi-squared is more inclusive than r-squared. R-squared is a linear regression per se, so you have your independent variable down here, x, you have your dependent variable y, because y is dependent on x to give you this plot. Okay, here you have r squared value of 0.74, here you have 0.6. Should have had more dots here, but this isn't a very good example, but this is a pretty good example of how r squared looks like with 0.74 correlation, right? Okay, chi-squared and linear regression. Chi-squared can be used in the context of linear regression, okay? What you have is you have the value calculated by summing the squared differences between observed and expected values divided by the expected values. Basically, that's like the standard deviation. Okay, Jordan Peterson on r squared values. Math, law, r squared is equal to 100% correct, 1. Like 1 plus 1 is equal to 2, that's a law, that's right all the time, 100% of the time. In chemistry, empirical science with low variables, r squared is about correct half the time. And in behavioral science like psychology or some behavioral program like Alcoholics Anonymous, where you have a lot of recidivism, you have a lot of people that go backwards, you got a lot of people that relapse. R squared is about, less than 0.3 or less than 30%. Or, it's wrong 70% of the time. But, it's Jordan Peterson said that you'd be lucky to get 30% correct. It's usually 10% or something like that because of the human and the stressors and environments of every human is too complex, so you could just say it's a test tube or law, right? There's all these multi-variables. Life of some humans is very chaotic. Hierarchy and IQ. In chemistry, you need at least a 130 IQ to be functional. Okay? Biology, you have a high degree of variables, a lot of chaos in biology. Chemistry, you have lower variables. Physics, you have the lowest variables. You have mathematical rigor in physics. Here you have empiricism, and here you have, a lot of handiwork to involve physics, biophysics, biochemistry, and physical measurements and instrumentation at the highest level to get results that are good and publishable in the photochemistry or photobiology or biochemical ed, biophysical actus, so you can get money from the government to proceed with your research in your lab given a PhD. Parametric equations, multivariables, where you have a whole bunch of independent variables. Venn diagrams, just the logical function. Ballpark figures, it's what the parametric equation after the treatment of a number crunching algorithm should give you, so that you know which ballpark or which particular parameter you're interested in and looking at a macro structure. Parametric equation, for example, here's a polar coordinate type diagram given more than one equation, more than one parametric equation, you put it in a polar coordinate system, gave you this. Here's an example of a Venn diagram where you have A and B, and what the intersected points in the middle is what A and B both have in common. It's one way to narrow down options. You could have 3, you could have 4, you could have multiple data sets, and the intersection thereof, it should give you an inference about the property or the commonality of the group dynamic. Okay, hierarchy modified. Differential equations is the queen of calculus. Calculus is the queen of algebra. Algebra is the queen of arithmetic. Basically, you need mathematics in order to even proceed with science. So you have physics, applied electronics and statics, chemistry, empirical synthesis, biology, use chemistry to test the macrostructure, and algorithms can be used to simplify all these things. Okay, an example as a case study is the ant. There's a research scientist at the UT Health Science Center in San Antonio that was a chemical biologist. He would make chemicals or poisons that would fit the antenna receptor sites of ants to disrupt the communication between one ant and the other, so the hive would not be able to communicate. They'd lose the communication with each other. The hive would thereby die, and you'd ameliorate the ant problem in a home, farm, or what have you, right? Thing is, there was a problem with the patent, there was a problem with the write-up of the patent, and the patent ended up being totally useless after all these years of research, and it got trolled out more than likely. So as a case study, basically never neglect the different parameters associated with your science. If you are a good scientist, that's one thing. Patent law is business, so that's a whole different genre, and you have to be astute in that aspect in order to make it work, right? There's all kinds of parameters that go into play that could always either help or hinder progress with respect to your will. All right. Hell, the topic was chaos structures and multiple variables, independent variables, parametrics, ballpark figures in science, and empirical work for results in the laboratory. You have to have an IQ of 130. That's superior IQ. It's not genius IQ, but it's good enough to get results done in the laboratory, but you need to be fairly intelligent in order to go about this from the get-go. All right, end of presentation.